go through the process. So they're kind of workshop series in a way. It's going to be an interesting exercise to go through. If anybody on here is interested in doing this in person, we have classes available in Tacoma, Redmond, Washington, and Everett. Those will be live workshop classes, or we'll have this format as well, or we'll do it via Zoom. So there's whatever's more accessible to you. We do have those options available. So that'll be March and April. And then May 24th, as we get into cooling season, talking about retrofits for refrigerant. We've talked about R22 retrofits for quite a while now, but now we're starting to phase down even newer refrigerants, and we're starting to do some pretty interesting retrofits with equipment. So that'll be a really interesting class to go through to kind of highlight where you're at now and where you're going, give you some options there. And then June is CPR and AED. That was a request from audience members from previous classes. And so we'll present the American Heart Association's hands-only CPR class. We'll do those in person at those offices I mentioned, and we'll do it via Zoom, which is something we're pretty adept at. We've been doing that through COVID. So it works out pretty well. It's not the same as being in a class with the Annie dolls and having that physical contact, but it's pretty good, and get people up to speed for summer, and maybe get to save a life. You never know. So with that, I'm going to turn it over to Joe Breathauer. He's going to kick us off with intro part 2. Joe.
Cool. All right. Thanks, Seth. So I don't know if everybody was here last time, but yeah, my name is Joe Breathauer. I've worked for MacMIller for the past 4.5 years. Before that, I did residential HVAC for about 3 years. So yeah, I've seen all the equipment we're going to talk about here. My experience is primarily with, VRF type systems. So we can go into that a lot. I'll let Brian, you introduce yourself if you'd like.
Yeah, my name's Brian Skelton. I'm in a very similar setup to Joe here. I've been with Mac for just about 3 years now. Before that, I did about 2 years in residential. Again, experiences on the service side of things, VRF, hydronics, building loops, stuff like that is going to be where I see most of my experience here. So if you do have any questions on any of that stuff, don't hesitate, reach out, ask. So we'll move on. All right. We'll start this off by talking about VRF. If anybody has VRF on their sites or has had any thoughts, this is definitely gonna cover the pros, benefits, why we would choose a VRF system over a more conventional system, and then what they look like and some of the components. So we'll start off here by looking at some of the components here. This guy on the left here is going to be our condenser outdoor unit. Just like any kind of refrigeration system, HVAC, AC, our goal here is to take heat from one spot and move it to another. VRF is no different. So we'll have an outdoor unit. Depending on the capacity, we may have 1, 2, 3, 4 units tied to one system. It just depends on what our implementation, our application is for our building. From our outdoor unit here, obviously we have to send our refrigeration piping to our indoors. Each space or zone, as we covered in our last class here, is going to be supplied with some kind of indoor unit that handles our heat exchange and our airflow throughout the space. Our indoor units can really be broken up into 2 classifications, and that's going to be kind of exposed or concealed here. So more traditional exposed systems are going to be like our wall mount unit here. And just like the name implies, we pick a nice spot on a wall and we mount it right there, and we either run our refrigerant lines into the wall or up into the ceiling where we can conceal them a little bit better. And we have our 1- and 2-way sealing cassette and our 4-way cassette here. Yeah. Okay. So we have our ceiling cassettes here. These are going to be exposed units. They're mounted directly into the ceiling. The difference between the 1 and 2 way and then the 4 way is really just the number of directions we're able to throw that air. So 1 and 2 obviously can throw it 2 directions. A 4 way can throw it in all 4 directions to supply space. Ceiling suspended system here is going to be very similar to a 4 way ceiling cassette or a 1 and 2 way ceiling cassette. And the only difference is
where we're going to be headed or what the union is going to ask.
the only difference is instead of being mounted in the ceiling, it's actually suspended utilizing something like all thread or some other form of support bracket. Floor mounted, same deal as wall mounted. The only difference is instead of being on a wall, right, it's mounted down on the floor. And then the last is going to be our ceiling concealed. And that is like its name, that's tied to ductwork. And we try and either hide that in a drop ceiling or in a finished ceiling, somewhere where we're not seeing it. We do have some applications where it is visible, just for the sake of we don't have a drop ceiling present. But normally these guys are more like a traditional air handler where we like to keep it up in the ceiling and out of sight. So any questions on those? Awesome. All right, moving on. So main points of a VRF system or variable refrigerant flow system. I know Daikin likes to call them VRVs, which is variable refrigerant volume. The reason why we have them is going to be it gives us true zone control, right? We can have multiple zones. If you look at the picture here, we have 5 indoor units. 1, 2, 3, 4, 5. The 2 on the left are in cooling. The 3 on the right are in heating. And that's going to be controlled by an individual thermostat for each zone. And VRV lets us have that individual control. So if we have, say, our zone 3, our middle guy here, we reach our set point, we're nice and warm, and then we decide we want to cool that space, we can easily kick that space on into cooling. It will switch into cooling and start cooling the space without interrupting any of the other zones. The other reason why we have VRF is efficiency. VRF systems are extremely efficient. And the reason for that is on a traditional system, we take heat from, say we're in cooling, right? We looked at our 2 guys on the left here. We're taking heat from our space where we don't want it. And on a traditional system, we would then move it to our outdoor unit where we get rid of it. We have to reject it, right? What VRF allows us to do is to not only move that heat from inside to outdoors or vice versa, but also between zones. So if we take a look at the system here, we have 2 zones here on the left in cooling. We have 3 zones on the right in heating. If we look at our outdoor unit here, this red line here is our high pressure gas, what we like to call our hot gas. When these systems are in heating, our outdoor unit is going to create hot gas, 120, 140 degrees, and it's actually going to send that gas over to these boxes here. These boxes are what we would call branch controllers or heat recovery units. And pretty much it's just a set of valves that switch between heating and cooling and allow us to have that individual control over our indoor spaces. Here we have hot gas coming in to our zone calling for heat, and it sends that gas through this rectangle right here. This is our coil. This is where our heat exchange happens. So our blower motor is going to push air across that hot coil. It's going to collect that heat, and it's going to push that into the space. What comes out of these systems is going to be a medium temperature liquid. Now, this medium temperature liquid is required for cooling operation. Now, normally we would just, on a traditional system, send this liquid back out. Absolutely, we can make these available for you guys. We can send this liquid back out to our condenser. And what that condenser does is that takes that liquid and that utilizes it to start making more hot gas. But because we have 2 zones in cooling, we can actually pull some of that heat energy off and utilize that for our cooling zones. So where we have our medium temperature liquid coming back, we have 2 zones in cooling that say, hey, I want some of that, I can use that without having to send that to our outdoor unit to expend more energy to create more hot gas. I can just utilize what we already have. And so it'll pull that liquid in to our coil. It goes through what we call a metering device, this little X right here, and that drops the temperature from a medium temperature liquid all the way down to a low temperature vapor. And then, of course, room temperature air runs across that cold coil. We get our cooling effect in the space, and then it sends our low pressure gas back out to the condenser. So it's really neat stuff, really helps us reach that high efficiency, get our true zone control. But also it's extremely flexible, right? Because if you saw on the previous slide, we have all these different types of units. It allows us to be flexible. If we have a branch controller in here that is already in place, and say we need to add another zone, or we're doing some kind of changes to the space, we can actually go off of that branch controller here, this branch box, and run another line set or copper refrigerant pipes to an indoor unit, say a wall mount or a ducted unit, anything have you, and actually add to that system. And of course, there's some minor adjustments that'll have to be made to the capacity of the outdoor unit, but it definitely allows us to have a lot more flexibility on that front. All right, now we have the types of VRF systems. There's two major contenders in the market. First one's going to be 3-pipe. The other one's going to be 2-pipe. Now, to my understanding, I think Mitsubishi is the only one that utilizes a 2-pipe system at this point. Every other ones that you'll come across, LG, Fujitsu, Daikin, they're all going to be utilizing the 3-pipe. That's the more traditional. As far as the operation, all VRF is the same process. The difference between the 2-pipe and the 3-pipe is where those processes happen. So with the 3-pipe system, I know we were talking about our high pressure gas or our hot gas. We have our medium temperature liquid, and then we have our low pressure gas. On a 3-pipe system, all of that is taken care of and supplied by our outdoor unit. On a 2-pipe system, our hot gas and our low pressure gas is handled by our outdoor unit, and then our medium temperature liquid is actually handled within our branch controller here. So it's same components, same technology. It's just instead of having it all done at the outdoor unit, we're moving some of it to our indoor unit. Main benefit of that is going to be cost for installation, really. It's one less pipe we have to run. So on a 3-pipe system, we're looking at 3 pipes we got to send to our branch controllers. On a 2-pipe system, obviously we're only sending 2 pipes through. I can, squeeze through tighter areas, less material costs for install. The trade-off is usually our branch controllers are a little bit bigger. So that's something that we have to explore. We got to make sure that wherever we're putting them, say a drop ceiling, a space, a hallway, a closet, something like that, it's got to be big enough to allow for that increased size there. And then we have VRF Hybrid. I've not actually seen one of these in the wild yet, but the principle of them is extremely cool. So what this allows us to be is as flexible as a VRF system is. A hybrid system allows us to be even more flexible. And the reason for that is if we look at the system here, we have our outdoor unit or our condenser unit. And then these green pipes here are our refrigerant lines. These are what's carrying our refrigerant, and it comes to our BCR branch controller, heat recovery unit, whatever manufacturer is calling it. And that's it as far as refrigerant. This branch box here actually acts as a heat exchanger for a water loop or a water system. So what that means for applications is that instead of having to run copper refrigerant lines to all of your indoor units, instead we're working with water lines. So these blue lines here and these red lines here, these are water lines supplying either heated or cooled water to our indoor unit. And again, the air passes over the coils and gives us either our heating effect or our cooling effect. As far as what that means for us on our end, Well, I can tell you from the service side, if we're only dealing with a refrigerant circuit going from an outdoor unit to a branch controller, that's a lot easier to maintain, troubleshoot, less capacity for refrigerant, only dealing with water. I don't want to say that's a safer medium, but that's obviously an easier, more environmentally friendly medium to maintain and handle, especially if we do have any issues versus having to deal with refrigerant lines going throughout the building. So really neat stuff. I haven't seen it implemented yet personally, but I would be excited to see what that looks like inside of a building. Definitely a step up from the traditional VRF. So. I'm going to hand this off to Joe. He's going to take over for hydronic heat pumps and hydronic loops in a building.
Cool. Sounds good. Before we move on, was there questions on VRF? I mean, that's literally like, I've been to I don't know how many classes and I still learn new things every time. So if it didn't make any sense, that's okay.
Yeah, you're not alone. It
Yeah.
takes time.
So cool. Well, I'll move on to hydronic heat pumps. And this is way more common. I'm in downtown Seattle, and this I would say is like predominantly what we work on down here. If you look at the picture over here, this is just going to kind of show you what a building would look like and have examples of different hydronic heat pumps. The red ones like this are going to be units that are in heat. The blue ones are units that are in cool. And then these are ones that aren't calling for heat or cool. But it's actually a very similar principle to VRF in that we can do heating and cooling simultaneously, and we're actually just transferring heat between the building. The way that works is if you look at any of these units that are in cooling, these blue ones, when you're in cooling, you're absorbing heat from the indoor air, you're putting that into the refrigerant, and that refrigerant is then putting that heat into the water. And I'll show you, there's a good diagram coming up next. I'll show you exactly where that takes place. But if we're in cooling mode, we're taking the heat from inside and we're putting it into the water basically. And what's cool about that is, well, that heat, if there's a unit in the building that's in heating mode, we can take the heat we just absorbed and then go over to a unit that's in heating. Because when a system is heating, it is pulling heat from the water and putting it into the air. So we're really just picking up heat from air here, dumping it into water, and then we're pulling heat out of the water and dumping it into the air in a different spot. You'll see on this as a boiler in the basement and a cooling tower up top on the roof. So we'll specifically dig into those. But yeah, the basics of a hydronic heat pump system is that the heat is transferred between water and air like it says on here. In cooling, heat is taken from the room air, and put in the water loop. In heating, heat is taken from the water loop and put into the room. Typical set points, and this will really vary depending on what building you're in, but a water loop is usually maintained between 60 and 80 degrees. You'll often hear us call that the condenser water loop. Normally your boiler would be set at 60 degrees. So if it gets, colder than 60 degrees, the boiler would turn on down in the basement and heat up the water. So the minimum temperature of the water being supplied to these units is 60 degrees. In the summer, when we're running AC and we're pulling a lot of heat from the air and putting it into the condenser water loop and heating it up, we have a cooling tower that makes sure our condenser water loop doesn't get above 80. So if it does, it'll turn on and reject that heat there. And then, yeah, just like with that VRF, that variable refrigerant flow, we have variable water flow. Let's just call it that. Yeah. So spaces can share energy. Okay. So the next slide here. So this is a pretty good diagram of a hydronic heat pump. When we keep talking about how the air absorbs energy and puts it into refrigerant, and then the refrigerant puts it into water, we're never mixing refrigerant and water. That's sometimes a common misconception. This right here, this little coil, we'll call that our heat exchanger. It's a tube inside of a tube. One tube runs refrigerant through it, and another tube runs water through it. And they're just conducting heat through the metal. They're not mixing, blending, doing anything like that. And if they are, you've got a failed heat exchanger and you got to fix that. Typically how the system would work, like let's say, for example, this system here is in cooling. We would have 75-degree air go over this coil. We have cold refrigerant running through our refrigerant coil, which would be this evaporator coil right here. The heat is going to go into the refrigerant, and then it's going to travel down and basically go into this water coil here, where we'll reject the heat we've absorbed from the evaporator, but reject it into the water. In heat mode, it stops it. If we want heating, we will pull heat from the water, put it into the refrigerant, and then put it into the air that's going into the space. So it's really just transferring heat from air to water, water to air, depending on what mode we want. I'm sure most people on here have a lot of hydronic heat pumps and experiences with them. So any questions so far? Okay.
It's interesting to note too that the biggest building in Seattle, Columbia Center, is all a hydronic heat pump loop.
Oh yeah.
It's not new technology, but done right, man, it can be very efficient.
Mm-hmm. Yep, especially during the times where, you know, half the building wants heat, half the building wants cooling, and then later in the day, the other half wants heat, the other half wants cooling. We get a lot of that, so we're a really good climate for it, and it's everywhere. So I'll move on to another type of hydronic heating and cooling, and that's geothermal. I personally haven't really worked on much geothermal, but I mean, the principle is essentially that, you know, the earth is going to stay a relatively constant temperature, and we can run water through that to reject or absorb heat. You can see some of the different types here, and really you gotta, it's not my expertise, but essentially you have to take into account the space, you know, how much land do you have? You see this big trough they dug to lay down a bunch of water lines. Sometimes they'll bore and go straight down a long ways. In this, they have like a pond, or you'll see people that have a stream and they'll run their water lines through there. Just a spot where you have a constant source of energy to either pull from or reject to. You can see one of the downsides, like what do you think would happen if, you know, one of these lines split? You know, how are you going to repair that? Right? You'd have to dig that whole thing up. A lot of times I know people just abandon it and run a new one. Yeah, we don't see a lot of geothermal around here, but that's essentially what it looks like there.
There's some older systems on Lake Washington, some old government buildings, NOAA, and some of that have where they've tossed slinkies out in the water. Same with down in Tacoma on Puget Sound and some of those inlets, but it's going into a large body of water isn't as popular as it used to be.
Cool. Well, that's we're going to move on to boilers. Before we do that, did anyone have any more questions about like hydronic units, or maybe you got some in your building you got a question about, or yeah, anything? Fire away if you got anything.
We got a request for the slide deck so that they can share them out with some coworkers, and I'll put that in the chat.
Okay.
I'll work on that.
Yeah, cool. Perfect. All right. Well, then I'll pass it back to Brian, and you can take over.
All right. All right. So boilers. I know Joe was talking a little bit about that on a condensing loop, right? If you're all running in heating, you're absorbing heat from that water. Eventually that water is going to dip below that 60-degree mark. That's where your boiler comes into play. So you'll have a thermostat mounted to your water loop and set for, 60 degrees. When it reads that it's below that temp, it'll fire away, right? Boilers in general have two categories. We have non-condensing, or what we call standard efficiency, and then condensing, which is a high efficiency, right? So non-condensing boilers are usually about anywhere between 70 and 85% efficient, right? So for every dollar you spend, you get 70 to 85 cents of heating out of it. Condensing boilers, I believe the highest I've seen is 98.5%. I believe that was the latest statistic. But yeah, 98.5. So 98.5 cents for every dollar you spend on heating actually gives you heating into your water. There is a trade-off to that. So starting with non-condensing, the reason why it's non-condensing is we're absorbing heat from we see our in-shop burner here. We see our little flame that generates heat to our heat exchanger. The water making contact with the heat exchanger, metal plate, what have you, it absorbs that heat. But we were still leaving heat on the table, if you will. And so the temperature of our flue gas or exhaust is still high enough that it's above our condensing temperature. So it's still hot enough that when you see it come out of our smokestack there, it gives off that shimmer, right? You definitely don't want to be touching that exhaust pipe. With condensing though, the big difference is there's actually a second heat exchanger. We actually call it a secondary heat exchanger. So if we look at our picture here, we have our primary, just like our standard efficiency or non-condensing boiler. And the water is absorbing heat from that. But then we continue on to actually a secondary heat exchanger there. And that water will still continue to absorb the heat content out of this flue gas. What happens is we absorb so much heat out of that gas gas temperature drops below our ambient condensing temperature. And so we start to condense, we start to get water. So you'll see on some bigger applications, it may be stainless pipe that's coming out. A lot of smaller ones, you'll see actually PVC pipe as an exhaust. And when you see the exhaust gas coming out of those, it's usually kind of a haze or a fog versus our non-condensing, which is a clear shimmer, right? Condensing is definitely the way to go as far as efficiency. However, that comes with something else that we have to address, and that being the water. See here, we'll skip ahead for a second. And the way we have to address that water here is we got to put it somewhere, right? So whether we're pumping it out through a condensate pump or we're draining it to a gravity drain to a floor drain or what have you out the side of the building, if our boiler is high enough that we can drain it through a wall. But being flue gas, right? It's combustion byproduct. That's not drinking water by any means. That water is very acidic. So if you look at this picture here on the right, that is a metal floor drain that has had a rough go of it. So what happens here is that if left untreated, that condensate, that water coming off of these boilers will start to eat away at the surfaces that they make contact with, which is definitely a no-go. We have to avoid that, and that's why maintenance on all boilers, but particularly on condensing boilers is so important here. And the way we do that, the way we maintain this water is on the left here. We'll see this tube of white pellets. That's actually a neutralizer. A lot of times you'll see it as these white pellets, or we may have a bucket of limestone rock on site that will go through, and we can actually test this water coming out of the drain. And if it comes back too acidic, we can actually swap out those rocks or those pellets with some new stuff, and that's going to help get rid of that acidity, treat that water, and make sure we're not damaging the surfaces that this water is coming in contact with. Stepping back here to these guys, this is just an example of what condensing boilers look like. So in this instance, we have 4 boilers set up. They're smaller footprints, smaller capacities, but they're set up in a way that allows us to stage them on and off, which again, just furthers our efficiency, right? So 4 boilers, depending on what amount of BTUs, what kind of heat we need added to that loop, what our demand is. We can stage on anywhere from just one of them to all 4 of them to anywhere in between. Allows us to have lower operating costs, smaller footprints. You'd be surprised at, especially some of these older hulking fire tube or water tube boilers, or standard efficiency ones, you'd be surprised at the size that you can see out of them. So definitely smaller footprints, better efficiency. The big downside to them though is obviously higher efficiency, the more advanced technology, if you will, they cost more. They're pricier, and that's just kind of the loophole there. They cost more upfront, and obviously they have more maintenance requirements, and therefore maintenance costs tend to be a little bit higher. But of course, the trade-off is with the increased efficiency, it's the operating cost over the life of that boiler is much lower than a standard efficiency unit there. So. All right, and then we have a fire tube boiler, non-condensing fire tube boiler. This is the big one here. So if we look here, and this is just a general example of the operation of one and how it works here. We have this guy here. This is our burner assembly. So this is what gives us the heat. We'll have gas feeding into this guy, and then we'll have some kind of ignition source, whether that's a spark generator or hot surface igniter, something that glows hot and ignites that gas, something to give us the flame, right? And it'll shoot our flame into our main barrel burner here. And if you look at this tank, this is called a fire tube burner. The reason it's called a fire tube burner is because the flame is contained within these tubes here, and then it's surrounded completely by water. So the way the operation works here is we have our flame comes in, goes through our main barrel here, hits our back plate here, and comes back in these smaller tubes here, travels through, comes back to our front plate here, and then this up here, right here, sorry, don't know if that was visible or not. This is our flue exhaust. So this is where our exhaust gas exits that boiler here. And so as this flame is traveling through these tubes, the water surrounding it obviously absorbs that heat in the same way you'd see with like a VRF system or a hydronic heat pump and that coil, right? The only difference is where those are, the medium is air passing through a coil. This medium is water making contact with the metal of the fire tubes and absorbing heat that way. As far as these boilers go, usually they're large, right? You get the condensing boilers. Those guys are going to be usually smaller footprints. The more traditional application that we see is going to be like those 4 units mounted in a way that allows them to stage. These guys, usually application, you're not going to see multiple ones of these installed. It's going to be, you got one big guy taking up space in a mechanical room, and it fires on when you want heat and kicks back off when that temperature set point is satisfied. With that, I know we were talking about fire tube. There's 2 main types of these kinds of boilers, and there's going to be fire tube and water tube. And we're touching a little bit on the fire tube. And as you can see with fire tube, as I was saying before, the fire, the flame, the heat, and the exhaust is all contained within these tubes. And then the water is actually completely surrounding them and filling up that tank. Let's see here. By the inverse there, the water tube boiler is the exact opposite. So water is contained within these smaller tubes, and then fuel, the fire, the gas, the heat completely surrounds these tubes. Now, looking at these, you would assume, well, it looks like I have more water in the fire tube, so that's probably a higher capacity than the water tube. But it's actually not. So generally speaking, a fire tube boiler is usually smaller, has a smaller capacity for its application. Usually see fire tube boilers in building heating, whether that's domestic water or condenser loop heating, stuff like that. Water tube boilers have a much higher capacity and BTU content there. We usually see these much less so in building heating scenarios. These are going to be more towards industrial applications, those kinds of processes. The trade-offs is water tube boilers are much more expensive upfront and much more expensive to maintain, whereas a fire tube boiler is cheaper cost, and then maintaining them is usually easier and cheaper over the life of these units. But again, capacity-wise, you get smaller capacity out of your fire tube versus your water tube. Did anybody have, I know that's a lot of information on boilers to throw at you guys. Did anybody have any questions about these boilers? If so, speak up, don't hesitate to interrupt. Otherwise, I'm going to
I have a
continue.
question about the condensate, like what causes it to be acidic?
The water coming off of that is combustion byproduct. So it's completely different. It's separated from the water that's going through your building and serving, you know, say it's serving domestic. It's not coming in contact with what is going out, coming out of your faucets and what have you. It is actually the byproduct of that combustion gas. So same as you know, the gas that comes off of a fire pit or a propane stove, stuff like that. It's all going to be a combustion gas, which is by its nature very acidic. So when it condenses down into a water, it doesn't lose that acidity. It takes it right on with it. It just becomes a water form.
Yeah, kind of an example too is like on a car. When you start a car up and the exhaust is cold, those hot exhaust gases hit that cold exhaust and then it condenses into a liquid and runs out the tailpipe. I think we've all probably seen that, especially during the winter. And those are burnt, that's burnt fuel that's you know, now exhaust, but it condenses into a liquid because the moisture content in the combustion process. And yeah, you wouldn't want to drink that either. But out of a car, you know, they generally make exhaust out of stainless steel for that reason, at least newer cars. And same thing in here with the boilers, except that our drains generally aren't stainless steel, so they don't handle it as well. That's why we have to neutralize it before it goes down the drain, or you end up with that picture that you showed of the drain cup.
Yeah, and the cooler the water that's coming back on the return loop to those condensing boilers, the better efficiency you're going to get, and the more condensing that's going to take place.
Yep.
So I've noticed that. I have some of these at my campus.
Yeah, if you can keep that return water to 130 or below, you can really take advantage of that condensing effect. And it's something like 1,000 BTUs per gallon of condensate that you get. So there's some real gains to be had there if you can manage your return water at that temperature. Real good for domestic, obviously, because groundwater is already cold.
Well, yeah, that'd be perfect for it.
Yeah.
Cool. All right. Don't think I'm muted. Can you hear me?
Yep.
All right, cool. So we'll move on. We're going to talk about chillers. And here it'll show you an air-cooled chiller and a water-cooled chiller. So we'll dig into that. You can see on this air-cooled chiller here, got this big refrigerant coil with fans on it. That's our condenser. That's where the heat that we're absorbing from the water comes up into this coil. This fan is going to run outside air through the coil, and we're going to reject heat from that refrigerant into the air and just get rid of it. We're just heating it up outside. We don't care if we're heating up outside. So for these chillers, the point of them is to cool down water, to deliver chilled water. A lot of times you'll have them delivered to like a fan coil unit or just anywhere where you're going to want cooling in the building. Yep, heat is absorbed. That equals chilled water. Typically, our water temps for your chilled water coils are going to be 35 to 60 degrees. That's pretty normal to see. Move on there. So this is going to show you what a typical air-cooled chiller setup is. This graphic's pretty good because it's going to show you we have our chillers outside where they can reject heat into the air. Our water is flowing through these chiller barrels. I'll show you right here, this like white line here is going to be warmer water that goes into the chiller barrel, rejects its heat, so it comes out colder. That heat that it rejected gets rejected outside, and then we're delivering chilled water with the use of these water pumps here down to some central air handlers on each floor that has like a chilled water coil where a fan blows air over the chilled water, and then that supplier will go into the ductwork and feed maybe some VAVs or different equipment in that space. So this would be that central plant thing we talked about where our cooling is done at a remote location. And then we're supplying all that cooling medium, the water inside. Here's a picture of a chiller that you can actually, it's a rental chiller. They brought it in on a truck, dropped it, and they were using this. It was purpose built. I know, Seth, if you wanted to talk to this, this was for the tunnel where they were trying to freeze the soil, right? When they were doing drilling.
That was for Sound Transit up by UW, that tunnel they dug. They bored the tunnel, they lined the tunnel, and then they used it to freeze the ground
Yeah.
in the middle of the tunnel. So they bored holes and put heat exchangers in kind of a horseshoe shape, froze the earth, and then they dug the earth out to make the escape tunnels out for people to get out in emergencies. So one of the common uses of rental chillers is to freeze earth. We did the same thing with the seawall replacement in Seattle down there along the piers. Froze the ground, took the seawall out, let the waves hit on the frozen earth until the new seawall could be built. And then they
Crazy.
yard the heat exchangers out, take the chillers away.
Yep. Here's going to be a water-cooled chiller. You'll notice it doesn't have that big refrigerant coil on it. It doesn't have all the fans. It's just the compressor. And you'll see a condenser barrel here and an evaporator barrel here. The evaporator is where we're going to pull heat from our entering water. We want to chill down that water and supply cold water out to the rest of the building. Well, when we absorb heat from that water, we have to reject it somewhere. So it puts it into the condenser barrel where we're able to reject that heat into the condenser water loop, which we were kind of talking about earlier. And then that goes up to a cooling tower, which I'll show you here. We'll go through that and we reject that heat outside. So these are typically a lot bigger. They're able to be installed inside. Yeah, they're going to look a lot different. They do require some different maintenance items than an air-cooled chiller. With an air-cooled chiller, you have to keep that condenser coil clean, make sure we got proper heat transfer through it. On these guys, we'll show you here. This is one of our technicians. Tube punching is what they call it. So these tubes are where water flows through, and actually in that barrel, you're going to have refrigerant surrounding it. But with water comes water treatment. And what we want to do is make sure that we don't have any dirt or grime or like bio growth. If your chemicals are out of whack and you're getting stuff growing in there, you don't want that coating these tubes and basically acting as an insulator, because if it acts as an insulator, we can't transfer heat across it. We can't transfer heat from the water to the refrigerant. And then you'll lose huge efficiency. You'll have all kinds of efficiency problems. You'll have pressure problems. Your compressor will have issues. It's just a cascading effect. So it has to get done all the time. You can see in that video just how much dirt is coming out of there. So, yep, you got to punch each of those tubes one by one. It's really thrilling work. But yeah, it's fun. It's crazy to see how much stuff comes out of them. This is a really good.
I was corrected by my boss. I got a new boss, and I said I was punching the tubes. He corrected me and said, "That's hydro lamps in the tubes, Ed."
Oh, that sounds smart. I like that.
So I have to use that now. I can't say punch tubes anymore.
Hydro lamps.
Yeah. Hydro lamps. That's cool. I'll make sure when I come to your side, I'm saying hydro lamps. Thanks for the warning.
Yeah, put in a side note there.
Yeah, hydro lamps. Write that down. That's fine. Yeah, so here's a pretty good graphic of just exactly how a water-cooled chiller works. You can see on one side right here, we have our hotter water returning to the chiller. We are absorbing heat from that water into the refrigerant, leaving the water cooler as it leaves. And then you have that cool water delivered to the air handlers. And then on the condenser side of this, where we're taking that heat that we absorb from the water, we're going to send that hot water up to a cooling tower where it's going to go through. And there are a couple different types of cooling towers we'll go through. But basically, that hot water goes up to the cooling tower where we reject the heat outside. And then we return that water to where it can pick up more heat and keep repeating the cycle. We're just moving heat. Okay. So this is going to be a picture of air handling unit on a roof, and this is going to tie in basically every single thing we've talked about so far. And I'll kind of just walk through just how the air would go through and what it can do. So when I say it's tying in everything we've talked about so far, I want to point to the fact that we have a chilled water coil here. So there's a chiller on this loop that's supplying chilled water to this one coil that is on this large air handler. This would typically be up on your roof and controlling all the air that's going into the building. It's going to control building pressure. You can see it has CO2 readings on it. So that's demand control ventilation. So we need to see, do we need to bring in more outside air? So yeah, we have a chilled water coil here. So there's a chiller. We have a hot water coil here. So there's a boiler. We have a heat recovery wheel here. So I'll go into that more specifically, but that's just a way to save energy when we're exhausting air. We don't want to just lose all that heat that we paid to, we paid to condition it. We've got our outside air. We've got exhaust. We need to get rid of air in the building. And then we've got our supply fan, and that's the tempered air going into the space. So the way I'll kind of walk through this is I'll start here at the return air. This is coming back from the building. So we're coming back. We go through a set of filters that's going to clean that air. And then we go through the fan, and there's a couple different things that can happen here. You'll see in this picture that our exhaust air damper is 20% open. So there's going to be a need to relieve some air from the space. So that's all air that's going to be getting put outside. We're exhausting it from the building. So a portion of the air here is going to travel through this heat wheel, and this heat wheel is going to absorb energy from the exhaust air. Let's say it's 70-degree air going through here. Well, some of that heat energy is going to be put into this spinning wheel, and as it spins, that heat then goes down here, and we'll get into what happens there. But we're going to harvest some of the heat from the building. Now that air passes through, goes out the exhaust, so we're dumping some air from the building. The majority of that air, because this mixed air damper here is 80% open, is going to go down here through the mixed air damper. And now we're going to pass through our mixed air sensors. So this is just detecting what the temperature of the air is. And there's also a freeze stat here. So, when we had our cold snap, we need to see, hey, if the air is, way too cold and we're starting to freeze, we need to start closing down our outside air, or, alarm that we could be running into a freezing situation where we'll burst coils, things like that. But that air then goes down through here, through the mixed air sensors. And in this case, we're actually calling for cooling. We see that because our chilled water coil is 56% open, and we can see that our set points, I got my Zoom stuff here. We can see that our set point is 17.2 degrees Celsius. The actual temp is 18.7 at this time. So we need to be cooling. So the air is going to pass through this chilled water coil, lose some of its heat into the water, and then be delivered to the space. At the same time, you'll notice that the outside air damper was 20% open. So there is some air being pulled in through the outside air here, and that's going to get filtered. We want to filter the air coming into the space. It's going to pass through these little cones here, which takes out a lot of the turbulence. And then that passes through this heat recovery wheel. Because we exhausted some air and recovered heat, that heat we're bringing back in, we'll pick some of that up. This is maybe not the best situation for it because we're cooling, but the principle is still the same. We just want to reclaim heat. So anyways, this is an interaction between all the different things we've talked about so far. We talked a little bit about ventilation, especially with COVID. We need a certain amount of inside air exchangers, so we have to bring in outside air. We need to consider the building pressure. We want a slightly positive building envelope. That way all the air coming into the space is controlled. So we're pulling it in from outside, and the building isn't going into a negative where you can't push the doors open. It's kind of hard, but we don't want the building under so much positive pressure that the doors are blown wide open, not closing, things like that. This is a lot to look at here, but I'm sure a lot of you actually have exactly this kind of display for some of your units at your buildings. And I guess one thing I didn't touch on is for this heat recovery wheel here, Like in cooling, you wouldn't necessarily be running it to recover heat from the space because we're trying to get rid of it. So in that case, you have bypass dampers where that shuts off and the air is just bypassing the heat recovery wheel.
There is always
Pretty
the case
so
though, like
far.
during the heat dome effect, where if outside air is 100 degrees, but your return air coming from your building is say 80,
Mhm.
I mean, that's a pretty good delta there. So to be able to kind of, you're pre-cooling the air coming in.
Oh
So
yeah, yeah, good point.
yeah, there are some benefits in both
Yep.
seasons.
Yep, absolutely.
And we're
Okay.
seeing a lot more of these heat recovery wheels were popular in the 70s and they died off for a while, and now they're back because of energy codes. And we see different versions. They're not all of them are spinning wheels. Some of them are fixed cells as well. But it seems like the heat recovery wheel does have a majority of the market,
Mm-hmm.
at
Yeah,
least
I've
in
seen a couple
commercial.
of them. Yep. Okay, so now we'll just move on and talk about cooling towers. When we're talking about those water-cooled chillers, and I kept saying it would, go to the cooling tower where we would reject heat. That's what we're talking about now. There are going to be two types of cooling towers we'll talk about. One is going to be an open style cooling tower, and one is going to be a closed style cooling tower. The first one we'll talk about is your open style cooling tower. And what that means by open is that hot water coming from the space, let's say we were on a building with hydronic heat pumps and they're all running AC and all putting that heat from the space into the water. Well, we got to reject that. So that hot water comes back from the building and then it literally dumps it over the top of this fill media here, where outside air passes through and we reject that heat outside. You'll typically see a lot of like steam kind of rising off the top of them. Downtown, you'll see that a lot. And then it literally falls down into the sump and returns back to the building. The biggest downside about having an open style cooling tower is that water that's circulating through your pipes is also exposed to the outside air. So it's exposed to all the car exhaust, just dirt, bird poop, anything you could think of that could possibly get into that water, gets into that water, and you got to clean them a lot, and they are gross. You have strainers that fill up. You can run into situations where the strainers aren't catching 100% of stuff. So then all that sediment and debris goes down into your pipes, then starts clogging up other strainers in your building. They're extremely dirty, but they're easy to install. They're the cheapest upfront cost. They're very efficient though, because you don't have any intermediate heat exchangers to try to reject heat through. It's just a direct hot water to the outside air, loses its heat, goes back into the building. But the downside is the cleaning of it. To me personally, I don't like them too much. I like a closed style cooling tower for the guy that's got to clean it. So here is the closed style cooling tower. And what that means is that our condenser water loop is never in direct contact with the outside air. So all the dirty contaminants. In this picture, our condenser water loop that's coming in from, let's say, the building again, that the hydronic building that's running all cooling and the water loop's getting hot. Well, it's going to come into this pipe here, go through and lose heat because we have it basically like an auxiliary water loop. We have a sump here of cold water that has a pump on it that takes that cold water to the top and then showers water down over the heat exchanger. So now you have your hot condenser water going through this metal tube that is rejecting heat basically through the metal to the outside water, and we're basically evaporating a lot of that water we're pulling from the sump. They're two separate loops. We're just raining water down on one. With that, you'll see mist eliminators. So a lot of that is so we're not wasting a lot of water, because when the cooling tower sump pump is running and pumping water down over our condenser water, a lot of that is going to want to start evaporating. And that's all that water is water you have to make up, you have to fill, and you got to pay to refill it. So you'll have things like mist eliminators, we call them, where it captures that mist, condenses it, drops it back down to the sump, so you're not paying for that. These still need to be cleaned. They don't get dirty nearly as much. You do have different components in them, like sump heaters that'll keep them warm during the winter so they don't freeze. You'll have water level sensors. You have a sump pump on these where you don't on that open style cooling tower. So there's going to be some more components to them, but the maintenance costs would be less. You don't have to clean them nearly to the extent you do on the others. And then you don't necessarily run into the same risks of pulling in all that outside junk into your pipes and clogging up your building. So I prefer them a lot more.
Yeah, something else to point out too, at least in Seattle and probably I think a lot of areas, when you pay your water bill, for every gallon of water that comes into your building, you automatically pay for a gallon of disposal sewage. And with a cooling tower, majority of that water that you pay for gets evaporated. So it doesn't actually go down the sewer system.
Mhm.
And so there's incentives out there to install what are called deduct meters. And they deduct the amount of water that you pay for from your bill. And so you actually measure the water that goes down the drain. So you're only paying for what goes down the drain. You're not paying for what goes up in the form of steam. So it's something to think of if anybody has cooling towers and they don't have deduct meters, which there's still a lot of them out there. Something to look into to help curb some of your water usage cost.
Yeah. Before we move on, does anybody have any questions? Cool. All right, pass it over to Brian.
Right on. All right, life safety or fire safety, however you want to call it. It's going to be our last segment here on the class, I believe. Yeah. So really what this is going to cover is how your HVAC system reacts during the event of a fire within your building to A, help contain the situation, and B, allow you the best chance to safely exit the building, right? So I know we talk about HVAC equipment. You'll hear some equipment tied to your fire panel, or I don't know if anybody's had nuisance issues with fire dampers that get stuck closed or fail closed, or a fan that's acting up, or a fire panel sensor that's not working right, or setting false alarms, stuff like that. But it's out there and it can be a nuisance, but it's there for a reason, for a very good reason. So let's take a moment to look at this picture here. Obviously, some stuff is going down on the 5th floor, right? We have a fire that broke out in the corridor. And your fire system, your sensors, your fire panel, that's all tied to HVAC equipment that is meant to serve your building in the event of an instance such as this. Looking at this picture here, we have this red guy on the top. This is what's called a corridor exhaust fan, and it does exactly that. In the event that we do have an issue, its job is to kick on and start pulling air out of that space. Over here, this blue guy here, this is what we call a stairwell pressurization fan, and just like the name implies, it does the opposite of our exhaust fan, and it's supposed to positively pressurize our stairwell. And then if you look here on each one of these floors, we have these little boxes here. These are going to be what we call fire dampers. And their job is to stay open when everything's fine. And then when it senses either smoke or heat, its job is to respond accordingly, either close down or open up. So in this instance here, we have a fire on the 5th floor. First thing that happens is our fire dampers on floors 1 through 4, they all close down. The damper on floor 5 stays open, and we energize our corridor exhaust fan. What that's going to do is that's going to put this space right here where our incident is occurring into a negative. And what we're trying to do here is we're trying to contain it. We're trying to keep that smoke from moving outside of the space, right? If we're in a negative, we're pulling air from other spaces in, versus being in a positive where we're trying to expel the air contained within the space out. So we're trying to contain that. On the flip side here, we have our stairwell pressurization fan. what that's doing is that is putting your entire stairwell into a positive pressure. And that sole job is to create a positive barrier. Again, like I said, with the corridor being in a negative, being positive, we're trying to expel air out. So if any of that smoke makes it out of that space, it's not going to migrate into our stairwell because it's going to hit that positive barrier, which is pushing back. So it's going to keep our stairwell smoke free and allow us the best chance to get down to the bottom floor and exit the building here. This is equipment that when we have maintenance, that is included on our maintenance. It's imperative that it gets done, but it is something obviously being tied to our fire panel where there is a little bit of coordination involved. We do have to get whoever your fire and life safety vendor is on site to coordinate so we can cycle these systems. These systems being directly tied to our fire system, if we try and override them and kick them on, it causes more of a headache and many more problems than we want to delve into. But just know it is important equipment, even if you do have nuisance issues, like I said, fire dampers getting stuck or what have you. It is extremely important to the building. It's something that we want to maintain. We want to make sure it's working. And there's obviously a little bit of coordination involved, but it is something that definitely, if it's not on your radar, please make sure it is. So, and then I believe our last slide to round off here is some examples of fire dampers for your viewing pleasure. You may see these in a variety of locations, office spaces. We see them again in stairwells, main lobbies, common areas such as elevator lobbies, building hallways, stuff like that. And a lot of them are tied to our makeup airs. So like I was saying, we have issues with them getting stuck closed. That usually comes in the form of, you have a 5-story building and we get a call in saying, man, floors 1, 2, 4, and 5 are fantastic. Floor 3 is stagnant, feels stuffy. It's hot. It's the middle of summer. That hallway is scorching hot. We're not getting any air. You go to the roof, you take a look at your makeup air, your HVAC's working flawless, right? But then we can go down and we can actually look at the ductwork where this makeup air is tied to, and we may find that one of these are failed closed. And whether that's an issue with a sensor or something with the fire panel, or even just a mechanical failure, a lot of these are run off of actuator motors that they can fail. Anything mechanical can fail. So another reason why getting these systems inspected and maintained is very important, because A, it's uncomfortable HVAC wise, right? It's stuffy. It's not comfortable to be in that environment. But B, in the event that we do actually have something go down where this needs to kick on and work as it should, we need to make sure that it's doing so. So with that, I think that is it, right? Yeah. This is the end. Anybody have any questions? Anything that they actually plucked out of that slew of information that we threw at you guys that you just had further questions on? Feel free to pipe up and ask. We're all ears.
Yeah, I put in the chat a survey link because we do value your feedback. I read every one of them. And that's how we pick what's going to come up next. We had some popular classes in the past, so we brought those forward for 2022. But we're always looking for input. So whether it's building controls, or if you want to look for indoor air quality, if that's a subject that's important, we can certainly slot those in as we go past our initial 6. Or maybe it's something else. I mean, we got lots of offerings. And then as I put in the chat, we do have some after hours classes that we do too. And we always invite customers and potential customers to attend those. So if that's something you can message back that you're interested in, if you want more information. But we're here to help you out. And of course, anything that you saw here today, of course, MacMIller installs and services. So we can help you out with any of those needs as well.
Cool.
So we'll stay on here for a little bit, but I think that's the end of Joe and Brian's excellent adventure.
Nice. Yeah, thanks guys.
Yeah, appreciate it. Thanks for coming.
Yeah, hope to see everybody for next month for the Clean Buildings Act and help save some energy on your buildings.
Yep.
Thanks, everybody.
Yeah, thank you.